Good afternoon. My name is Ian Arbon. I'm chairing this afternoon's event on engineering for climate change. This is arranged by the Energy, Environment and Sustainability Group of the Institution of Mechanical Engineers. I have the great privilege of being a founder member of the EESG some 21 years ago, and a past chair of it as well. We have a very packed programme for you this afternoon, so I'm not going to take any further time out. But we're also greatly privileged to have not only our President of the Institution of Mechanical Engineers, but also our Chief Executive of the Institution of Mechanical Engineers with us in the room today.
So good afternoon, everybody. We have in the room probably about 15 or possibly 20 people here in Glasgow, and then, from what I can make out, there's 30 or 40 online. So thank you for inviting me, and I hope I can make a small contribution to your event. I'm here today, obviously, because of the COP26 summit or conference. It is very appropriate that we should be using this as an opportunity and using it to support the work we're doing on our impact on society. And what could be more powerful than engineers helping to improve our society? So today's session looks very interesting. There are 3 papers, as you know. I'm looking forward to hearing them, and I hope that all goes well.
Next presentation is a joint presentation from Daniel Kenning, who's here with us, and Susan Krumdieck, who's remote.
Hello, I'm Daniel Kenning. I'm a mechanical engineer and transition engineer, and I run Splendid Engineering. I'm also a member of the Energy, Environment and Sustainability Group of IMecHE, and I'm very happy to introduce Professor Susan Krumdieck, who is online in Orkney at the moment. Hello, Susan.
Hi. Yeah, I'm a mechanical engineer, and I'm an academic in transition engineering at Heriot Watt University in Scotland.
And Susan and I are the co-founders of the Global Association for Transition Engineering.
Right. And in the next 30 minutes, we are going to answer the question, how do we achieve those net zero targets and take action and save the planet? Well, let's start with the fundamentals, right? Let's put forward a case for the future where the targets for net zero were met with plenty of time to spare. It's a believable thing, right? If that's true, then something happens. Something happens now that is new, that hasn't been happening yet. It breaks the business as usual plan. It results in 80% reduction in fossil fuel production and use as required by climate science. And as long as we're proposing this theory, imagine that the result of this radical change also grows our social capacity, regenerates our biocapacity, regenerates our biodiversity, and builds resilience and equity. Wouldn't that be okay?
Okay, so the facts are, if we look at the fossil carbon dioxide that is now in the atmosphere, nearly all of that got there through successfully operating and legal and profitable engineered systems. So all those molecules got there through what we do. And that's what we call economic growth. However, all the evidence, especially the evidence of atmospheric CO2 levels, shows that all the efforts since the 1960s to solve this problem, and all of the COP meetings, of which this is the 26th one, have made no difference at all to this relentless trajectory. And the industrial technical enterprise just keeps racing along the same trajectory.
Right. So the question that we wanted to answer, how do we change everything fast? That's a really good question. The climate emergency is clear. That's what these meetings have been about for more than 30 years. What isn't clear is how do we change direction and go the way that the climate scientists are saying we have to go? How do we change not only what we're doing, but the value proposition of what we're doing?
Okay, so clearly the job we have to do is to change course, and this is what transition means. It means changing direction. So we have a system, the technical enterprise, which is actually working. Everything works. Everything goes fine. The trains work, the cars work, the factories work, the lights work. It all works. But it's going in the wrong direction and it's heading towards danger. So this diagram of railway points illustrates that the two things that we engineers have to do is to, first of all, get off that track that we're on, because that leads to danger, and the current trajectory lacks the all-important capacity to continue. It cannot continue. So the first thing we need to do, disruption, get off that track, and then the second thing is to identify a new trajectory and a new way. So that's the two things we're trying to do to get towards safety.
All right, Daniel, that sounds great. But every one of those changes that you want to make involves changing what we're already doing that works and changing what uses fossil fuels. And every time I work on one of these problems, what happens is that we understand it to be wicked. A wicked problem is when you're not trying to change in the way we have been for the last 70, 80 years, which is to make things bigger, make them better, make them faster, less expensive. We're trying to change something that already is all those things into something that uses 80% less fossil fuel. And the wickedness of it is that it already works great. Now, of course, we know it's not sustainable, and it's not even that hard to figure out what's not sustainable about it. It uses more fossil fuels than we can use right now, right? But there's a really big problem here, and that's that we are meeting our needs with this thing, and the people meeting their needs don't know how else they would do it. And so that is going to stop our discussion pretty quick. But, you know, the scientists and environmentalists, they're going to come up and say, you know, that's causing so many problems. And again, we'll get stuck just looking at the problems. So we know we want green solutions, but we don't really want those green solutions to be about change. We just want something to relieve this pressure of the need for change. And we don't want to even think about what would happen to our essential activities and goods. Because even though they might be able to be met, we don't know how. And so we want to use what works great. So we get caught in this spinning wheel of death, really. It's like when you ask your computer to do something it doesn't want to do, it just spins. And that's where we're at with wicked problems. And everything that uses fossil fuels is one of those. And so it's really the first step in transition engineering is to understand when you've got one of these wicked problems, sit down and parse this out and recognize there is no quick solution to this. You have to do something else. This is a complex, wicked problem. It's got lots of parts that intertwine. It's tied up with other systems. It's complex. And so answering that question of how do we change everything quick? What we know about wicked problems is that 1,000 reasons why you can't change it right now will fly up and stop progress. So,
so as Susan says, so the thing is that in the past, massive changes in the industrial technical enterprise in systems that were not broken, that were working, massive changes have happened in the past. Lots of times. For example, in 1911, the whole industrial technical enterprise was working just fine, but factories, vehicles and products were dangerous. They were unsafe. And every year, 100 and so years ago, thousands of workers died at work. And at first it was accepted as the price of progress. It was accepted until it wasn't accepted. And when it wasn't accepted, in 1911, engineers got together and effected the emergence of a new discipline, which we now call safety engineering. And because of that engineering initiative, and that emergence of a new discipline, which you can call a corrective discipline, thousands of lives are saved every year. And that happened over 100 years ago. So it can happen again.
That's right. If safety engineering hadn't happened 100 years ago, if you stayed on the same trajectory of worker deaths per unit of industrial good, you would have 8,600 worker deaths a year now in the UK. Today, there's less than 200. Those 8,600 deaths that would happen without safety engineering occurring would all be just the price of progress, things we couldn't change because, well, what would you do? And now those 200 deaths are not acceptable. So something really changed, and it was safety engineering. Safety engineering is the first really solid instance of the emergence of a corrective transdiscipline. Okay, you all know what corrective means. A transdiscipline is really interesting because it's not its own discipline. In a way it is, but it's also a discipline within every field. And every field has its own ways of expressing this thing of safety engineering. Now, safety engineering started in 1911, as we said, and it started with 62 mechanical engineers who got together after a terrible incident that killed 140 young girls in one day, the Triangle Shirtwaist Factory fire. And they decided to just do their job but not kill people. And they decided that in order to do that, they would have to be honest about what the problems are and what the possible solutions were. And to me, to think about what was going on at that time in 1911, that they thought the most important thing that they as engineers could do was to be honest, that really resonates with me as somebody who's worked on hydrogen and carbon capture and things that, you know, I want to be honest now. I want to tell people what the probability of that working is. And I want to be honest about what the problems are. It's that we're burning too much fossil fuel. And I find those two pieces of honesty quite hard. I don't know about the rest of you. The other thing that they decided was to prevent what's preventable. All right, I'm showing you this picture of linesmen doing their job in a very profitable industrial technical enterprise, and the rate at which these linesmen were dying on the job was faster than the rate at which they could be trained. So this was not a nice place to work. And safety engineering wrote down this nice phrase, prevent what's preventable. All right, you look at those guys and you think, what's happening? Well, they're getting electrocuted and they're falling to their deaths. And if you look at what a linesman looks like today, you'll see that the engineering that was deployed to prevent what's preventable isn't something you had to go to Mars for. It was normal, everyday types of engineering, materials, mechanics, dynamics, power engineering, physics. All right, they deployed engineering that they could immediately to prevent what's preventable. And you know that there are a million of these examples of engineering in practice. Yes, there's some research. Yes, there's some experts, but there's transdisciplinarity. There's everyone thinking, how would I prevent that? How would I do this? What could I do about this? What could my company do about this? So the idea of safety engineering is to do your normal work, but with the duty of care for workers' lives and health. And that is not a surprise to us anymore, but 100 years ago it was. It changed really fast, though. Safety engineering grew so fast. And this ethos of changing successful systems that work very well, thank you very much, if they must be changed, that was applied in all fields within about 30 years, and it was a sticky idea that kept going.
So this diagram here shows, this is an inspiring model that shows that the principles of safety engineering on the top line there, they were developed, I think there's some dates on that diagram as well, isn't there, Susan? I think. That's it. So in 1911, safety engineering was developed. It was developed by engineers. It wasn't actually developed by politicians setting targets that the engineers followed. It was the engineers leading. And they just set out to apply the principle that Susan has mentioned of just doing what needed to be done without people dying. And this similar process has happened over history every time a big successful system turned out to be disastrous, either for people or for the environment. So what we're doing now is proposing a new corrective transdiscipline, which we call transition engineering. And this is the way to make something really big happen right now, and quickly, that will change the industrial technical enterprise. So we have this method to do what needs to be done, but with 80% less fossil energy.
Right.
Back to you, Susan.
Yeah. And so I think you're all maybe along with us at this point because you're aware of all these transdisciplinary fields of engineering. You're aware of what they do, how many lives they save, how many disasters they prevent, how they improve resilience. And you're thinking, well, yeah, could that kind of thinking be applied yet again to the biggest disaster we've ever seen so far? We think so, and so if you want to be a part of this, probably the next question you're asking is, okay, how do you do that? And our answer is relatively simple. You use a method. All right. If you remember, there's things like free body diagrams, there's, drag relations. There's all these methods that we use to do hard things in engineering. And for about 20 years, my research group and others around the world have been working on, okay, how would you do this? How would you engineer change where change is not actually wanted, but it's warranted? And the answer came out of all that research, published journal papers, more than 50 papers, and working with Daniel and others in practice to see, okay, how would you apply it? How would you do it? And the methodology is called the interdisciplinary. Remember, we said it's transdisciplinary. Interdisciplinary transition, because you're going to change something. Innovation, because how you're going to change it isn't actually known right now, or you would just do that. Management, because it has to make money, and engineering, because it's an engineered system that has to change. It doesn't matter what your carbon tax is, an engineer still has to do something. All right, so the methodology has 7 steps. Why does it have 7 steps? You can read the journal papers and find out. It has 7 steps because it works. So if you imagine that you're faced with one of these wicked problems and it has no solution, it's horribly complex, and at every turn, people just actually don't want to talk about this anymore. They want to go talk about some cool technology they saw on the internet. Okay, can we all get together, stakeholders in this particular project, in this particular problem, and let's go back and look at history. So step 1, we look at history. Why? Because there's not that many arguments there. We can all learn something, and we can learn together and start to build our stakeholder relations around finding out, has this wicked problem always existed? 100 years ago in 1911, did they have this same problem? How did they meet their needs? What were the businesses like? What were the policies like? And we just find out. It's not a judgment thing. We're just learning history. And then we start looking as we come forward in time, what changed? How did those changes affect things? How much of it was engineering change? How much was social change? And what we'll start to see by looking at past dynamics is how this system works. And it works that engineers change something, people use it, policymakers regulate it, somebody in business sells it, and engineers change something again. So really, when we change something, the rest of the system adapts to it. Therefore, we can change something in the way it needs to change and know that everything will adapt to it. So we then study, okay, well, what's going on at the moment? Get good data, get good information, get facts. That's the present study. Then we look forward a little bit to see, okay, what do we think is going to happen next? What are the stories people are telling? What are the ideas they've got? And we test those out with engineering analysis to see, do they actually solve the problem? Or are they part of the problem by being distracting? If we find that the things that keep stopping us in this wicked problem, the green solutions we're hoping for, but that just never come, are really part of why we can't solve the problem, then we need to just set them aside, park them for a while, and we'll come back later. Let's get innovative. How do we get innovative? We apply the constraints that we know are the requirements, and then we take a little time travel. Now, that's a whole skill. If you want to know more about it, you can learn easily, but it's the funnest part. It's not like visioning. It's an engineering visit to 2121, where we see that wicked problem has indeed been solved, and how are people getting along doing stuff. And that lets our problem-solving brains go off the chain. Then we come back, do backcasting, you know what that means, and then we design a project. And this is where we use the insight that we got from this whole project. We use the perspectives of all the stakeholders, and we develop a project that we can do in the normal way that changes the direction. There's our transition mechanism of how we change things. Now, there is one more piece, and that's step 7, which is to look forward for unintended consequences. We're going to do that this time because, good step to include. All right, so that's our method, and I don't think it's too complicated, and it's quite colorful. So you think you could do that?
So there you are. You see, that's the method. We've got this methodology, and this has been developed over many years, 10, 20 years, as Susan was saying. And we've been asking ourselves for 10 years, how can engineering help bring about change to unsustainable systems? And we've been asking, how do we take action? And as Susan has mentioned, there's steps you can take. And I promise you that diagram, it might look complicated, but the 7 steps, after a while, you'll memorize them. They're easy to remember, and it makes complete sense. So we've been working out how to answer the questions of how to achieve sustainability or the capacity for continuity by getting the correct problem definition, exploring the history, creating a new way, as Susan said, time travel into the future, and collaborating with all professionals and academics. And these are things that you can all do now. Everyone on this call can do those things right now. It's not difficult. So it's something that can be done now straight away to deliver. If I pinch the words from David Attenborough, this is what can be done to turn the tragedy into a triumph, and it can be done quickly.
Right. I agree. And we're going forward. And we're bringing as many people as we can with us. There's a fundamental method. There's tools. There's approaches. There's economic analysis that's quite different, and that's all been published now in the first Transition Engineering Handbook, and that came out just before COVID, so it's quite new. And there's ongoing research into more transition tools and methods, and that stakeholder process that we talked about. It's worked so far, but we want to get better at it. And that's why I'm at Heriot-Watt University, because we're setting up a master's in transition engineering, a research program. And actually the research program is to achieve the net zero transition in the Scottish Isles by 2030. So we're gonna just get stuck in there and do this. That's what we believe. We can do this. There are already management and exec ed opportunities possible for those processes for leaders and for teams. There's already online courses in transition engineering that receive micro-credentials and CPD credit. Daniel's offered CPD around the world, and there's, like I said, already online. And some folks in the UK have done a lot of work, and they've set up a actual professional organization. The first one's that is transdisciplinary. And it's called the Global Association for Transition Engineering. And we invite everyone to have a look at that. And there are engineering consultancies in transition engineering, and a lot of engineering consultancies that are, especially their young engineers, sponsoring them to take these courses, get trained, and start working on transition for clients.
Basically, there's tools there available. And basically, all of you listening and all of you online, you can do this right now. So it's there to be done. So please join us.
Yep. And it doesn't matter which field of engineering you're in, you can work on changing what needs changing in your field by becoming a transition engineer. And why do we think, okay, when we set up GATE, it was funny because we thought there needs to be another thing, another organization, another, action group. Like like we need a hole in the head, right? Another action group isn't going to change anything. But then when we started thinking about what transition engineering really is, that it's another one of these transdisciplines, that if we didn't start it, the first 62 of us that got together, if we didn't start it, we're going to just continue going to the future we don't want to go to. So because it's a transdiscipline, everyone can become a transition engineer. It's not an elite group. It's not an outside crowd. So yeah, thanks for listening to our explanation.
Well, thank you very much, and very useful and interesting talk. It occurs to me that we hear a great deal at the moment about the energy transition. It seems to be one of the most popular buzzwords of the day, but we hear very little about how that's going to be engineered. And so transition engineering obviously has a very major role to play in this. And I think it's absolutely appropriate that we are highlighting it in this event. So thanks again for that excellent presentation.